Good afternoon, ladies and gentlemen. My name is Anren Gao. Come from Shanghai Institute of Microsystem and Information Technology in Chinese Academy of Sciences. So this work is done by my colleagues, but for some reason he can't come to give this talk, so I will give it instead. And the title of the presentation is Research on Self-Test Method based on Thermopile infrared sensor. First, I will give an introduction of the background, then is the design and the fabrication of the infrared sensor, then the device performance was characterized, and finally, I will give a summary. So for the Thermopile infrared sensor, they have many applications. They have now been widely used in some areas like muscle guidelines, satellite attitude control, infrared imaging, and also some gas sensors. Of course, they have many advantages. They can be operated at room temperatures. They don't need any wires and electric excitations. They also have CMOS compatibilities. This will make their sensors to be fabricated very simple and cost effective. Although there are many studies on the infrared sensor, there are still some problems to be solved currently. The two main problems. The first one is the higher infrared performance is also needed for their applications in some specific areas. And the second one is the lack of the self-tester mechanisms. Because of the lack of the self-tester mechanism, if we want to know the performance of the sensor, whether it works well, we have to measure it with very complex equipment. So of course, it's very expensive and maybe time consuming. So a simple and convenient self-test method for the infrared sensor is highly desired, and this work will report this method for the IR detector here. First, let's take a look at the principle for the Thermopile infrared sensor. This kind of sensor, it works normally based on the Seebeck effect. Seebeck effect is normally a thermoelectric phenomenon for the potential difference between the two materials, as shown in the picture, material A and material B. These two materials has different Seebeck coefficients. If they are connected at the hot junction, and the hot junction is heated, a voltage can be measured at the cold junctions. So the output voltage can be calculated with these formulas. This formula, in the formula, the N is the number of thermocouples and alpha is the Seebeck coefficient difference between the material A and B, and the delta T is the temperature difference between the top hot junction and the cold junctions. So based on the principle of the Thermopile infrared sensor, we have designed an infrared sensor which also have a self-tester mechanism. So this is this picture shows the schematic of the designed sensor. As we can see, we use the N-poly and P-poly silicon as the thermocouples, as shown in the picture is green and purple. In the center area is the silicon oxide and the silicon nitride. They are the absorbing layer and the structure support layer. At the final, this area is dry etched to be freestanding. This yellow part is platinum heater. If we apply a voltage between these two electrodes, the heater the temperature of the heater will increase. So the hot junction was heated, so we can get a voltage at the cold junction. The device was fabricated with the following procedure. I will explain. First, we deposit the silicon nitride and silicon oxide, and finally the polysilicon on the top with the LPCVD. And then the polysilicon was doped with phosphorus and boron to get the N-type and P-type polysilicon. Then the undoped poly was etched by RRE, and after that, the aluminum was used to interconnect the thermocouples. After that, we fabricate the platinum heater in the center here. And finally, the etched windows was opened and the thermopile structure was released. This SEM picture shows the finally finished device. We have successfully finished the fabrication. So after the fabrication, the device was tested first with the standard measurement. This setup includes the black body, the triple amplifier, and the digital oscilloscope. The black body is set to the degree. The frequency of the triple is set to 4 Hz. The amplifier factor is 1240. So this picture shows the voltage response of the thermopile infrared detector. As we can see, the output voltage is 0.2507 volts. By using standard formulas, we can get the device responsibility and the detectivity as these two numbers. The frequency response of the detector is shown in this picture. As we can see, the 3 dB cutoff frequency is about 102 Hz. And by using a formula, we can get the response time of the sensor to be about 2.5 milliseconds. So these 3 factors, the responsibility, detectivity, and the response time, is the 3 main factors for the thermopile infrared detector. So we compare the performance of we reported in this work with some representative works have been published by other workers. As we can see in this table, this work has better performance than other works. We have analyzed some reasons for our good performance. For the high responsibility and detectivity, we think we use the highly doped N-type and P-type polysilicon. They have large Seebeck coefficient and very small thermal conductivity. And we also designed the etching windows. They have very good thermal insulation but doesn't affect the complete release of the whole structure. For the salt response time, we use silicon. It has very small thermal capacitance than the aluminum that used in the references. And in our design, we designed a heater in the center of the device. The heater is very close to the hot junctions, so this may accelerate the transfer of the heat from the absorption area to the hot junction. So this may be the reason for our short response time and high responsibility and detectivity. And finally, the self-test measurement of the Thermopile infrared detector was conducted. We don't use the standard setup just mentioned because it includes the complex equipment. We just use this heater at the center. We use different input power. You can get the output voltages that is linear with the input power. So we developed this self-test method for the Thermopile infrared detector. So this method is very convenient and also effective to monitor the sensor performance. We don't need the complex and expensive equipment, and we can know whether the sensor works well. It's very easy and effective, convenient. Finally, I give a summary. In this work, a CMOS-compatible Thermopile infrared detector was designed, fabricated, and characterized. This infrared detector has high performance, high responsibility, detectivity, and short response time. We have also designed a self-test for the IR detector. This self-test method will provide an effective way for performance monitor of the thermal-based devices. May be also used for other thermal devices. Okay, thanks for your attention. Have you any questions?